Lecture 10 is all about the method of trigonometric substitutions. Sometimes an integral contains an expression that looks like one of these three, and in that case, sometimes it makes sense to make one of the following substitutions. It's important that you learn which substitution to make in which circumstances. So suppose I have the square root of a squared minus x squared, then the substitution x equals a times sine theta works, where I'm assuming theta is between minus pi over 2 and pi over 2. In other words, I'm making the substitution theta equals sine inverse x over a, but it makes more sense here to make the reverse substitution by replacing x by a times sine theta than to try to figure out what happens when I directly make the substitution theta equals sine inverse x over a. In this case, I use the identity 1 minus sine squared theta equals cosine squared theta to simplify this expression. If I have the square root of a squared plus x squared in my integral, then it sometimes simplifies the integral to make the substitution x equals a times tangent theta. And again, I choose the theta in the domain of the restricted tangent function so that theta is tan inverse x over a. And the identity 1 plus tan squared of theta equals secant squared of theta makes this expression much simpler to deal with. If I have the square root of x squared minus a squared, then I make the substitution x equals a times secant of theta, and I choose the theta appropriately so that it's in the domain of the restricted secant function, and essentially I'm making the substitution theta equals secant inverse x over a. Although we haven't studied this function directly, it suffices to know that theta is secant inverse x over a, and secant of theta equals x over a. When I make this substitution, I use the identity secant squared theta minus 1 equals tan squared theta, which is just the previous one rearranged, in order to simplify this expression. Let's look at an example. Suppose I want to integrate x cubed over the square root of 4 minus x squared. Then I claim the substitution x equals 2 times sine theta will work here. Here, of course, a squared is 4, so a is 2. And now the square root of 2 squared minus x squared should be the square root of 4 minus 4 sine squared theta, which should be 2 times the square root of 1 minus sine squared theta, which is 2 times the absolute value of cosine theta, but because of the way we chose theta, the absolute value of cosine theta is actually cosine theta. So I let x equal 2 times sine theta, and I have the square root of 4 minus x squared. So the square root of 4 minus 4 times sine squared theta. Pulling out the 2, it's 2 times the square root of 1 minus sine squared theta, which is 2 times the absolute value of cosine theta, which is 2 times cosine theta, because of how I've chosen the angle. Now the dx, this expression becomes simpler, but the dx becomes more complicated when I make this substitution. So I get dx d theta is 2 times cosine theta, so dx must be replaced by 2 times cosine theta d theta. And now, of course, x cubed must also be replaced by 2 cubed sine cubed theta. And I get my integral is 8 times sine cubed theta by dx, which is 2 times cosine theta d theta, over 2 times cosine theta. The 2 times cosine thetas cancel, and I'm left with 8 times the integral of sine cubed. Then I can use my substitution, and I end up with an integral of the form, the answer becomes 8 times cosine theta cubed over 3 minus 8 times cosine theta. At this point I must convert back to x's, so I must check what my theta is equal to in terms of x, because x is 2 times sine theta, then I have theta is equal to sine inverse x over 2, because I've chosen the angle between minus pi over 2 and pi over 2. So I can replace theta here by sine inverse x over 2, and this is my solution. Now, I would rather, if that solution didn't have trig functions in it, and remember when we studied inverse trig functions, we figured out how to convert an expression like this to an expression in x by using a triangle. So to get an expression for cosine sine inverse x over 2, I create a right angle triangle with an angle theta, which is sine inverse x over 2. In other words, sine of this angle is x over 2, the opposite over the hypotenuse, and then the third side is the square root of 4 minus x squared. So this expression can be replaced by the square root of 4 minus x squared, the adjacent over the hypotenuse here, over 2. And this means my integral now becomes 8 times that cubed over 3 minus 8 times that. And that's equal to, when I tidy it up, 4 minus x squared to the 3 over 2 over 3 minus 4 times the square root of 4 minus x squared plus c. I can make the same substitution here. I have a different a, so you can play with that before class. Here's the second type of substitution. So part of learning this method is recognizing which substitution to use, and then of course carrying out the substitution. And in this case the recommended substitution is x equals a times tangent of theta. And of course dx will then be a times secant squared of theta d theta, and we'll get the square root of x squared plus a squared will be the square root of a squared tangent squared theta plus a squared, which is a times the square root of tangent squared theta plus 1, which is a times the absolute value of secant, which is just a times secant of theta. Because of how theta is chosen, the absolute value of secant is secant here. These calculations are always the same whenever you make this substitution, so it's good to keep that in mind whenever you're using this method. Here we let x equal 2 times tangent theta, a is equal to 2. Again, dx is 2 times secant squared theta d theta, and the square root of x squared plus 4 gets replaced by 2 times secant of theta. And that's about it. That's all we have to replace in this integral. So we have the integral of dx over the square root of x squared plus 4 is 2 times secant squared theta d theta over 2 times secant theta, which is the integral of secant theta d theta, and that, as we saw the last day, is the natural log of the absolute value of secant of theta plus tan theta plus c. And now, of course, the fun begins when we replace theta by tan inverse x over 2. Remember here, x over a is equal to tangent of theta, and theta is in the domain of the restricted tangent function, so theta is tan inverse x over a. And now we'd like to translate the secant of tan inverse of x over 2 to an expression in x, and once again we use the right angle triangle. We create one where we have an angle where the tangent of the angle is x over 2, and then we figure out what the hypotenuse is here. The tangent is the opposite over the adjacent, so square root of x squared plus 4, and then we're looking for secant of theta, and secant is 1 over cosine, so it's the hypotenuse over the adjacent. So we can replace this expression by this expression in x, and then our answer looks much neater. Notice that if I have the integral of 1 over x squared plus a squared, which I already know is 1 over a tan inverse x over a, I could also make this substitution to figure that out, but it's maybe better to remember that integral. Sometimes you have to complete the square to apply this. That's an extra little twist that you might have to use. And our last substitution is x equals a times secant of theta. So remember, you have to first be able to recognize where to use each type of substitution. And in this case, if we have the square root of x squared minus a squared, we use x equals a times secant of theta. And again, the calculations are the same. The square root of x squared minus a squared will always be a times tangent of theta, and dx will always be a times secant theta by tangent of theta d theta. So there should be no surprise in calculating these two things in your integral. Suppose I have the integral of 1 over x squared, square root of x squared minus 25. Here the a is 5, so I'll let x equal 5 times secant of theta. Dx is 5 times secant theta, tangent theta d theta. And then the square root of x squared minus 25 becomes 5 times the square root of tangent squared theta, which is just 5 times tangent of theta because of how the angle was chosen. And now my integral becomes dx, which is 5 times secant theta, tangent theta times d theta, over x squared, which is 25 times secant squared theta, times the square root of x squared minus 25, which is 5 times tangent of theta. Many things cancel, and I'm just left with 1 over 25 times secant theta d theta. That looks a little scary, but remember, secant is just 1 over cosine, so I turn that 1 over cosine upside down, and I end up at 1 over 25, the integral of cosine of theta d theta, which is really a trivial integral. So I get 1 over 25 sine theta, but remember that theta is secant inverse x over 5. So to make this simpler, sine of secant inverse x over 5, I must appeal to my knowledge of right-angled triangles once more. So I put this theta equals secant inverse x over 5 in the corner of a right-angled triangle, and secant of that theta must be the hypotenuse over the adjacent, which is x over 5. That allows me to calculate the length of the third side, which is the square root of x squared minus 25. And now sine of this angle, sine of secant inverse x over 5, is the square root of x squared minus 25 over x, the opposite over the hypotenuse. Then I can substitute that for this complicated thing everywhere in the integral, and I end up with a nice answer written in terms of x.